Picture this, a world where nuclear power is safe, clean, and abundant. Sounds too good to be true. Well, it might not be, thanks to a little-known element called thorium. Intrigued? You should be. Welcome to the Clean Energy Journey YouTube channel, where science meets sustainability. We share how green energy will save our planet in the future. Today, we're diving into the fascinating world of thorium and its potential to revolutionize sustainable energy. As the global community grapples with the urgent need to transition away from fossil fuels, thorium has emerged as a promising alternative to conventional nuclear fuels. This element offers a unique combination of safety, abundance, and reduced environmental impact that could bridge the gap between renewable energy sources and traditional nuclear power. So, what exactly is thorium? It's a naturally occurring, slightly radioactive metal found in the Earth's crust, and it's actually more abundant than uranium. Unlike uranium-235, which is commonly used in nuclear reactors, thorium itself isn't fissile. This means it can't sustain a chain reaction on its own. However, inside a reactor, thorium can be converted into uranium-233, which is fissile and can be used as fuel. Compared to uranium, thorium boasts better physical stability, produces less long-lived radioactive waste, and is more evenly distributed worldwide, potentially reducing geopolitical tensions over energy resources. The story of thorium in nuclear energy isn't new. In fact, thorium reactors were first tested back in the mid-20th century, with notable experiments conducted at Oak Ridge National Laboratory in the United States. These early tests showed promise, but uranium-based reactors ultimately became the standard. Why? Well, during the Cold War, uranium reactors had a distinct advantage. They produced plutonium, which was valuable for nuclear weapons programs. As a result, the global nuclear industry was built around uranium, and thorium research was largely pushed to the sidelines, despite its potential benefits. Now, let's talk about how thorium reactors work. One of the most exciting designs is the liquid fluoride thorium reactor, or LFTR for short. Unlike traditional reactors that use solid fuel rods, LFTRs dissolve thorium in molten salt, which circulates through the reactor. This innovative design allows for higher operating temperatures, improved efficiency, and inherent safety features like passive cooling. Perhaps most importantly, LFTRs can continuously breathe thorium into uranium-233, creating a self-sustaining fuel cycle that produces minimal waste. The advantages of thorium are truly impressive. First and foremost, safety is a major selling point. LFTRs are designed with passive safety systems that significantly reduce the risk of meltdowns. Addressing one of the biggest concerns about nuclear power, efficiency is another key benefit, as thorium fuel cycles can extract more energy per unit of fuel compared to uranium. When it comes to waste, thorium reactors generate smaller amounts of long-lived radioactive materials, making disposal easier and less controversial. And let us not forget about abundance. Thorium is 3 to 4 times more common than uranium in the Earth's crust and is found across multiple continents, ensuring a stable and accessible supply for the long term. Of course, no technology is without its challenges, and thorium is no exception. There are significant technical hurdles to overcome, particularly in designing and scaling LFTRs. These reactors require advanced materials capable of withstanding high temperatures and corrosive molten salts. The financial aspect is also daunting, as billions of dollars would be needed to develop and commercialize thorium technology with uncertain returns on investment. Additionally, the existing nuclear industry is built entirely around uranium, so transitioning to thorium would require massive changes in fuel supply chains, regulations, and reactor design standards. When comparing thorium to uranium, several key differences emerge. The fuel cycle is distinct, as thorium requires conversion to uranium-233, while uranium-235 is directly fissionable. In terms of waste, thorium generates fewer long-lived actinides, those pesky radioactive elements that cause so much concern, while uranium reactors produce large quantities of plutonium and other hazardous byproducts. Safety is another area where thorium shines, especially in molten salt designs that operate with inherent safety features, reducing meltdown risks compared to uranium reactors that rely heavily on active cooling systems. As we look towards a sustainable energy future, thorium could play a crucial role in complementing renewable sources like solar and wind. While these clean technologies are excellent for generating electricity, they depend on weather conditions and storage solutions to provide consistent power. Thorium reactors could step in to provide stable, carbon-free energy around the clock, ensuring grid reliability while reducing our reliance on fossil fuels. Together, thorium and renewables could form a balanced, sustainable energy system that meets our growing power needs without compromising the environment. The global effort to develop thorium technology is gaining momentum. China is leading the charge, with an experimental molten salt reactor in development that could pave the way for commercial thorium power. India, with its vast domestic thorium reserves, is actively investing in the technology as a path to energy independence. In the United States, interest is resurging, though funding and political will remain limited compared to other energy priorities. Europe is also in the game, with several research initiatives underway, particularly in Norway and the UK. The future of thorium depends on continued investment, international collaboration, and breakthroughs in reactor technology. So, can thorium be the foundation for the next era of sustainable energy? The potential is certainly there. Thorium has the power to reshape nuclear energy into a safer, cleaner, and more sustainable option. However, the road ahead is not without obstacles. Financial, technical, and political barriers must be overcome before thorium can take its place in the global energy mix. But if these challenges can be surmounted, thorium could play a central role in providing low-carbon energy for the 21st century, bridging the gap between renewables and reliable baseload power. As we wrap up our journey into the world of thorium, it's clear that this element holds immense promise for our energy future. While it's not a silver bullet, thorium represents a compelling path forward in our quest for sustainable clean power. The challenges are significant, but so are the potential rewards. As we continue to explore and develop this technology, we may find that thorium is the key to unlocking a new era of safe, abundant, and environmentally friendly nuclear energy. Thank you for joining us on this exploration of thorium and the future of sustainable energy. Remember, the path to a cleaner planet is paved with innovation, determination, and a willingness to explore new possibilities. Until next time, keep your curiosity burning bright, and stay tuned for more exciting discoveries on the clean energy journey.